let's move on. Now that we know how to draw Lewis structures, figure out the formal charge for each atom in the Lewis structure, okay, we can now talk about some of our exceptions to the octet rule. Now, we've seen many exceptions to many of our concepts so far in our lessons, so of course we're going to have some exceptions to our octet rule. So remember, our octet rule is everything wants 8. That's again, 8 is great. Oops. Helps if I could spell great. But with our exceptions, we're going to see that not 8 is also great. So sometimes we're going to have more or less than 8. So when drawing Lewis structures, up until now we have been obeying the octet rule. However, with many topics we've seen up till now, there are exceptions. So we have 3 different exceptions to our octet rule. So those are 3 different categories. Our first exception is a version of an incomplete octet. Where the central atom has fewer than 8 electrons due to a shortage of electrons. Okay, a shortage of electrons. This we typically see in elements early in the periodic table. So I have the example here of beryllium. We see it with hydrogen as well. Hydrogen, we know, only makes 1 bond to have 2 electrons, so it doesn't obey the octet rule. Okay, we have the example of beryllium here. If we look at how to draw our Lewis structure of BeH2, well, beryllium has 2 valence electrons plus the 2 valence electrons from the 2 hydrogens. I only have 4 electrons to work with, so I don't even have enough electrons to create an octet. So my 4 electrons are strictly going in making those bonds. So I just don't have enough electrons to complete my octets. So we only see this in elements that don't have enough electrons. So this would specifically be hydrogen, lithium, beryllium, and boron, as well as aluminum. Okay, so those are the elements that we typically see this in. Not every element can have a shortage of electrons. If you have extra electrons from your counting, then you have to put them into the structure. You can't just throw them away. So this is specific for these 5 elements. So let's prove this. Let's just double check that we can prove this with our compound boron trichloride. So we have to practice our naming here. Boron on our periodic table is B. Trichloride, well, we know chloride is chlorine, so that'd be Cl, and the tri means 3, so BCl3, boron trichloride. So we take our valence. Boron has 3 valence electrons, it's in group 3, plus the 3 times the 7 from the chlorine. Okay, so that gives us a total of, what's that, 24 electrons to work with. So I have some electrons to work with. So let's see. We next follow up with our steps. Boron is in the middle. It's bonded to the 3 chlorines. I used up 6 electrons to do that, and I have 18 electrons left over. My next step says to complete my octets. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Minus 18 electrons to give no electrons left over. Now, boron does not have an octet, but if we remember our rules, halogens don't like more than 1 bond. And this is typical, this is a general overview of halogens. We're going to see some exceptions to that as one of our exceptions to our octet rules, but if we can avoid it, then that's fine. And the reason why we're able to avoid it is because boron it has an incomplete octet. Okay, I have no electrons left. Boron just strictly will not form any double bonds. This is because it's so small, it only has 5 protons. So if I tried to make any double bonds or anything like that, it's just overloading that nucleus with too many electrons, and it doesn't balance out the charges very well. So boron is fine having only 3 bonds. We also see this with, BH3, where I only have 6 electrons to work with. So BH3 looks like this. I use up all 6 of my electrons, making the structure, making the bonds, but this is an acceptable structure because I just don't have any electrons left over. Okay, so boron is one of those that is fine having an incomplete octet. Our next exception is again another version of an incomplete octet. But it's specifically where we have, where the central atom has fewer than 8 electrons because it has an odd number of electrons overall. So we've looked at a lot of Lewis structures so far, and all of our valence electrons that are contributing to bonding have always been even, and if they were odd, we usually had a charge that would change that. But in some cases, like the example of just NO2 without a charge, okay, we have for our valence electrons 5 from the nitrogen plus 2 times 6 from the oxygen. That's a total of, what's 12 plus 5? 17? 17 electrons total. So if we look at the electrons in this structure, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So I've accounted for all 17 electrons. I've followed my rules for bonding in this structure. Okay, my rules for Lewis structures here. But I just have an odd number of electrons in my total number of electrons. So 1 electron just won't be paired up. So that's the 1 electron on the nitrogen. A molecule that has an odd number of electrons are referred to as free radicals. So this specific exception is referred to as the free radical exception, where we have an odd number of electrons. It's still an incomplete octet because the nitrogen only has 1, 2, 3, 4, 5, 6, 7 electrons. But it's because of an odd number of electrons, not because I didn't pair my electrons up correctly. And that's called a free radical. So we don't see these often. They are very rare, okay, because electrons really do prefer to be paired up. So if we have a case where we have 1 electron that's unpaired, it will typically be removed, and that's how we get an ion. So another version of this that we've seen in this lecture was NO2 plus, where we saw the structure for that, and it didn't have a free radical. So typically we don't see free radicals that often, so just keep that in mind. Okay, the most common exception is our last one, and this is a central atom that has more than 8 electrons, and this is called an expanded octet. So it has more than 8, expanded. This can go up to 10 electrons or 12 electrons. It will not go any further. Okay, so 10 electrons or 12 electrons around the central atom. That's where it stops. It's not going to go any further. It's not going to have 14, 16, 25. It's not going to have any more than 12 electrons. Okay, so it's either 10 or 12 electrons around the central atom. Okay, so here we have SF6. Okay, sulfur hexafluoride. And we can see that because there's 6 fluorines, I have to accommodate them somehow. We know that fluorines only like to make 1 bond, so the only way that we can do that is put all 6 of those fluorines on the central sulfur. Okay, so the sulfur now has to accommodate 6 bonds corresponding to 12 electrons around it. So it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons around it. So expanded octets mean that they have more than 8 electrons, and this only happens in atoms that are in and beyond the 3rd period. Okay, so everything from period 3 down. So this is going to be sulfur, phosphorus, chlorine, selenium, bromine. Let's see, let me write some of these down. Sulfur, phosphorus, chlorine, selenium, bromine, iodine. We can even have the noble gases getting in on this. Okay, they can now form expanded octets. Okay, so, and this is because everything in group 3 has access to a 3d orbital that they can utilize to accommodate these extra electrons. So in everything from in row 2, what we were talking about before with the proton or the nucleus being so small, not having a lot of protons, well, as we get a larger and larger nucleus with more and more protons, we can accommodate more electrons, and we accommodate them in the d orbitals. Okay, so that's why these are able to occur. We know that there is no 2d orbital if we look at our orbital chart from back in chapter 4. We could check that, but there is no 2d orbital. It starts at 3d. So because these elements are in row 3 and down, they have 3d and 4d orbitals that they can accommodate the extra electrons in. Okay, so let's look at a few of these. So let's follow our Lewis structure rules and draw the Lewis structures for the following compounds, and then determine which exception it falls under. So exception 1, 2, or 3. 1 being incomplete octets because there's not enough electrons, 2 being incomplete octets for free radicals, and 3 being expanded octets. Okay, so first we have HO2. HO2, let's follow our rules. HO2 has 1 valence electron from the hydrogen, and then there's 2 oxygens which each have 6, so we have 13 electrons total. So our structure becomes H, O, and O, right? H can't be our central atom, so oxygen will be. So that oxygen will have 1 oxygen and a hydrogen bound to it. So I used up 4 electrons to do that. That leaves me with 9. So I'm going to fill in my octets. So hydrogen is good. I'm going to do my oxygen out here first because it's my surrounding atom. I used up 6. I have 3 electrons left. They go 1, 2, 3, which means I have no electrons left over. So since I've been dealing with odd numbers, I had an odd number of electrons here in my count. We know that this is going to be exception number 2. The incomplete octet with a free radical. So we have this 1 electron that's unpaired. So that's a free radical there. So if you see an odd number of electrons, they're not going to pair up because you don't have enough electrons. So it'll automatically be an incomplete octet with a free radical. Okay, let's do our next one. Al-I3. Aluminum is in group 3, so it has 3 valence electrons. And then I3, there's 3 iodines, each have 7 electrons around them. So that is 24 electrons total. We have Al with an I on each side. So that used up 6 electrons. I have 18 left over. I'm going to use those to complete my octets of my iodine. So I used up all 18. I have no electrons left, and because aluminum is in group 3, it is fine with exception number 1. an incomplete octet. With too few electrons. I just don't have enough electrons. Now I'm not going to form any multiple bonds because the halogens would prefer not to form double bonds, and group 3 elements don't prefer to form double bonds either. So that could be another rule that you add to your rules of atoms. Boron and aluminum don't like to make double bonds. They like single bonds. They like 3 single bonds and that's it. Okay, our last example is PCl5. PCl5, phosphorus, has 5 valence electrons. We have chlorine, which is going to be 5. There's 5 of them, and they each have 7. So that's 40 electrons. We have so many electrons. Okay, so phosphorus is in the middle. It's going to bond to chlorines. Okay, I'm going to try to make it as compact as possible. Okay, so I had to make 5 bonds to accommodate all of those chlorines. So that was 10 electrons total. I have 30 electrons left over. I'm going to use those to complete my octets of all of my chlorines. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. I used up all 30 to complete my octets. I already had more than an octet on my phosphorus, so I don't need to worry about that one. So this would be an exception for number 3. An expanded octet. Okay, so those are our 3 structures for our 3 exceptions to our rules. The exception that you are going to see most often is going to be exception number 3, expanded octets. So for our last set of practice, I want to take some time and practice drawing these Lewis structures for all of these molecules which have expanded octets. So you're going to expect to have more than 8 electrons around the central atom in each of these molecules. So what I want you to do is pause the video, follow your Lewis structure rules for each of these molecules, and try to draw their Lewis structures, each with expanded octets. Following the rules will still result in the expanded octets because you just have so many electrons that you're going to be working with. Okay, so try these on your own and come back to the video to check your work, or if you get stuck, to get unstuck. As we said before, the noble gases start being included when we start talking about expanded octets. So they can start to form structures when they have expanded octets. So if we look at our first example, XeF4, xenon tetrafluoride, we have 8 valence electrons that are coming from the xenon, and there's 4 fluorines, each with 7 valence. So in total, we have 36 electrons to work with in this structure. So we start with xenon in the center, and it's going to bond to 4 fluorines. Okay, so I made 4 bonds with 8 electrons. So I have 28 electrons left. I'm going to use those electrons to complete my octets on all of my fluorines. So that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I used 24 electrons to complete my octets, and I have 4 electrons left over. Now, if we follow our rules for Lewis structures, it now says to place any remaining electrons on the central atom as lone pairs. So we're going to take these 4 electrons and put them on xenon as lone pairs. Okay, so we're still following our Lewis structure guidelines, no different for these exceptions to our octets or anything like that. We're still following those guidelines. The guidelines will then allow us to show that we can have expanded octets. So our xenon has an expanded octet because it has 1, 2, 3, 4 bonds, which is 8 electrons total, as well as 2 lone pairs, which is in total 12 electrons around it. So our xenon has an expanded octet with 12 electrons around it. Okay, let's try another one. Let's try selenium tetrafluoride. So very similar to the one that we have right now. Our structure is going to look a little bit different, but selenium tetrafluoride is 6 valence from the selenium and 4 times 7 from the fluorines again, which is a total of 34 electrons. So it's going to look very similar to what we just did. So we're going to have selenium in the middle, 4 fluorines around it. We know that to complete their octets, we have to use, let's see, we used up 8 electrons. We have 26 left. To complete the octets of the fluorines, we needed to use 26. Or sorry, 24 electrons. I used up 24 electrons to complete the octet. I have 2 electrons left over, so those 2 electrons are going to go on my central atom of selenium as a lone pair. So still following those rules, 1, 2, 3, all the way through to the end. With expanded octets, though, we are not going to be forming multiple bonds. No multiple bonds. We've already surpassed our octets. We don't need to form multiple bonds because the rules tell us, our very last rule is if octets are not complete. Well, with expanded octets, the octets are complete with some extra electrons in there. So we don't need to make any double or triple bonds. So we will not see any double bonds in here or triple bonds or anything like that. So don't think that this lone pair now needs to go onto here to make a double bond. It won't happen because our rules, again, are halogens prefer not to have double bonds. Okay, so when we're having expanded octets, we do not form multiple bonds. Our last example is XeOF4. So very similar to what we did in our last 2 examples now, but we now have an oxygen thrown in there, so that's going to change a few things. So let's count. Xenon has 8, oxygen has 6, fluorine again has 4 times 7. That is a total of 42 electrons. That's a lot of electrons. Let's draw it over here on the side. We have xenon in the center. Now we're going to have an oxygen and then our 4 fluorines. I'm going to do a fluorine here. 1, 2, 3. How am I doing this? 1, 2, 3, 4. There we go. I can fit all of them. Fitting all of these with an expanded octet takes a little bit of practice. Okay, so I made 5 bonds, so I used up 10 electrons. So we then subtract off 32, or so we're left with 32. I'm now going to use my extra electrons to complete my octets. So I'm going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So I used 30 electrons to complete my octets. I have 2 left over, which I'm going to put on my xenon because it can have an expanded octet. So that is our final structure for xenon. Xenon with an oxygen and 4 fluorines. No specific name for that, at least for the place that we're at right now. Okay, so if we look at this, if you look at this structure, you may think, okay, well, the fluorines are following our rules, halogens only making 1 bond, but oxygen is not following its rule. But if I were to try to move one of these, because oxygen prefers to have 2 bonds and 2 lone pairs, if I tried to do that, that would create a multiple bond in my structure. But with expanded octets, There are no multiple bonds. At least for what we're doing. Are there exceptions to that? Sure, there's exceptions to everything. But for what we are learning about, we will not have any multiple bonds forming with these expanded octets. Okay. So that completes our lesson on Chapter 6, our second lesson of Chapter 6, where we talked about formal charges and exceptions to our octet rule in Lewis structures. So before you move on to your next chapter or your next exam, please make sure that you finish the ALEKS homework and master the concept of formal charge and expanded octets, or exceptions to the octets, before moving forward.